طيب بسم الله الرحمن الرحيم. So last time we just talked about some introduction about wireless and mobile applications in general, and we started to talk about the challenges for wireless communication in general, regarding device portability and for battery operated device, and we discussed some issues related to power consumption and things like that, because the fact about mobility sort of dictates the battery operated the battery operation of these mobile devices. Because if I want to be portable and move, if I want to be mobile and move from one location to another, I cannot be hooked up to a power outlet. So I need to be autonomous and move from one location to another, which also enforces the fact that I should use batteries. The fact that you use batteries makes it even more challenging. That power may actually drain, and in that case you need to be very alert and very efficient in terms of using the power. So today we will cover some fundamental characteristics for wireless signals that really affect, for example, the device portability, the power and everything. So we will talk about some fundamental features and characteristics in the wireless signals themselves, and particularly when it comes to specific bandwidth or specific frequency ranges of these power signals. So we need to know that when we talk about this frequency range, what does this imply in terms of characteristics on the wireless signal? In terms of how long does it, how can the wireless signal travel along the distance? Is there any restriction to penetration of walls, things like that? What is the what are the factors that affect these kind of things in the wireless signal? So, so wireless in general, wireless networks in comparison to fixed networks, they have really very specific characteristics. Of course, wireless signals, they suffer from high loss rates, and we will discuss the reason for this in details, but now I think we can appreciate easily that because of the interference, because of the fact that wireless signals, they travel across the air, so they have more possibility of other sources and other obstacles and other environmental objects and things that interfere with this. For example, if you have even microwave at home, microwave works in the same frequency range, believe it or not, that Wi-Fi operates in. So microwave can actually interfere with the Wi-Fi, depending on the channel that you use. So this interference causes the wireless signal to deeply fade away, in which case the wireless signal that arrives to the receiver will be very weak, that the receiver cannot really construct the data represented by this wireless signal, in which case we get some packet loss or we get some loss rates. So the interference and the fading in the wireless signal causes some high data loss. So any emission, engines, lightning, all these sources, they actually affect the wireless signal, because the wireless signal travels through the air. Well, if we have a line, the electric signal goes through that line. Okay, so the possibility of other sources, other external sources affecting the electric signal that goes into the line is low, right? But since the wireless signal travels across the air, the possibility becomes really high. Okay, واضح? Okay. So restrictive regulations of frequencies. It's very challenging because, as we said, the only way for us to mitigate and to kind of control this interference is to try to move the signal in the frequency domain from one frequency domain to another. Okay, like for example, we know that microwave works in this frequency range, so we will try to change the channel on Wi-Fi to work in another channel or in another frequency range. So this way we can control and we can reduce the interference. So we know that, that's good. However, you cannot just work in any frequency range as you like, right? There are certain regulations that restricts that, okay? So there are some organizations, some world organizations that control the use of specific frequency. And they control that not on the user level, they control that from the manufacturer level. So you cannot, as a manufacturer, manufacture any wireless or mobile device that uses specific frequency ranges. Okay? So, and this is because they want to have like high-level control on the interference between the different devices and the different things that use like any kind of wireless signal or any kind of signal. Okay? So there are some strict restrictive regulations on these frequencies, and they have to be coordinated. And particularly in wireless, this is really hard to coordinate, because as we said, wireless, you have tons and millions of wireless devices, and the possibility of these devices interfering with each other is high. So we have to really conduct that coordination between the different frequency ranges really carefully. Okay? Right. Lower transmission rate, of course, the fact that the wireless signal travels through the air, there is a possibility that not only it interferes with others, but the fact that the wireless signal immerses in different directions through the air, there is some attenuation that happens to this wireless signal, right? So the fact that this wireless signal attenuates, it makes the transmission rate for wireless signals really in the low level. So the only way to increase, not only way, yeah, one of the ways to increase the transmission rate is by consuming more power. So you transmit with higher power. If you transmit with higher power, then the wireless signal will travel longer distance. If the wireless signal travels longer distance, then it reaches to other receivers with high possibility and high success rates, and that allows you to to elevate the transmission rate. However, to do that, you need high power, and also because of the fact that the wireless signal attenuates fast. So the wireless signal travels through the air. So you can. So if we. So if this is the distance, the wireless signal, it can go like this way, and then throughout the distance it kind of attenuates. So if the receiver, this is the distance, huh? So if you receive the wireless signal here, if you have an antenna and receive it here, there is a possibility you can receive very good signal, and in that case you can receive everything that gets sent from the sender. However, if you try to receive something here, the signal would have been weakened a lot, and then in that case there is a high possibility of distorted signal, which will lead to lower packet rate or lower transmission rate. So this is the inherent problem for the case of wireless that does not, again, exist in wired, and that's why we need to design the wireless devices carefully. So the wireless signal, typically, well, we will go through the evolution of the different mobile communication standards, and we can see that it can go from a few kilobits per second in the case of 2.5 G, and all the way to nowadays we're talking about ranges of gigabits per second, which is really a huge elevation of data rates for wireless. But to do this, the design is really complicated. But the typical rates that you can get using earlier standards of mobile communication was in the range of 53 kilobits per second, which is not really enough to support video applications and some applications that really require high data rates. Okay. So nowadays we're talking about hundreds of megabits per second with LTE. So we'll talk about these technologies and the differences between these technologies that led to the fact that we can go from 53 kilobits per second all the way to hundreds of megabits per second on wireless, which is phenomenal. But to do this, you require really sophisticated design of hardware and software and drivers and things like that. But it's really hard. Of course, as you can imagine, that for wireless signals, if the signal weakens fast, there is a high possibility again that packets will not arrive. And if you use something like TCP, what happens? For TCP, if one packet is dropped, what do? You retransmit. You send it again. Okay. So packet loss will be transmitted or will be transformed into delay, really. So if you use TCP, you do retransmissions. That's fine. You will resolve the packet drop, but you are introducing extra delay, right? So you're not solving all problems. You are solving the problem of packet drop, but you are introducing other problem, which is packet delay. And guess what? I mean, for some applications, especially multimedia applications, like if you're talking about YouTube and the delay is really sensitive. It's actually for video video is more tolerable to packet loss more than delay, and that's why many of these technologies, they don't actually use TCP. If packets are lost, okay, that's fine, because the eye will average out the scene and will give you good quality, even if there is some few pixels here and there that are not shown correctly. So the eye will average it out. So so delay and jitter. Jitter is actually delay variation. So so if you have a sender and you have the receiver, and of course there is some network in between, so there is one packet one. If packet one goes through the network and arrives here as packet one, so the delay is what we call the end-to-end delay, right? So what is jitter? Jitter is different from the end-to-end delay. If you have packet 2, okay, then packet 2 will arrive here, and not necessarily using the same gap that they left the source. So the network here may actually introduce some variation in the delay of each packet. So for example, packet 1 encounters 200 milliseconds delay end-to-end, but packet 2 may encounter 300 milliseconds packet delay. Why? Because it may go through different route, it may encounter more fading, someone is passing by and he faded the wireless signal, many things, okay? So packets inherently may encounter different delay, and that's what we call delay variation or jitter. So jitter is particularly important for multimedia applications. And of course, as you can imagine, wireless has many sources of distortion and interference and stuff, which makes delay variation really high. So you may get delay variation in very long ranges, and that causes a packet jitter, which is really bad for multimedia applications. So imagine if you are watching a game and then the guy says goal and you don't see anything because, well, the video information did not arrive yet because there is some pause and the network or the wireless network is actually congested, or there is some fading and stuff. So the effect of jitter is even more sensitive for the case of multimedia applications. So so of course, again, wireless introduces a big challenge for the case of delay and delay jitter. Okay. Security. Well, security is really challenging for the case of wireless. Why? Well, because again, I mean, for wired, the signal is going through a wire. So in order for you to tap into this communication, you have to cut the wire and get inside, right? Whereas for wireless, you cannot control anyone who's listening to the wireless signal. The very famous example, which I always give to people, is that about a few weeks back, I landed into New York Airport, JFK, and my credit card got stolen. So somebody with a small device reader, he read my credit card information while I'm passing by. So yeah, nowadays hacking is getting really sophisticated. You could do that. And by the time I reached the hotel, I found like many transactions on Facebook, and it was really scary. That's because, well, wireless signal, it travels through the air. Anyone can listen to it. They are talking about a very famous scenario now that if you have your car is keyless, of course it works in very short range. If somebody walks behind you, you can actually get the wireless signal from this and replays it through long distance to another guy who is next to your car, and he can open the door and get in and drive the car, and they can steal the car just by getting the wireless signal, replay the wireless signal. They call it replay attack. So wireless signal is prone to all types of hacking and attacks. Why? Because wireless signal travels again through the air. But the fact that the electric signal in wires goes into a very deterministic path, this makes it hard to hack or to attack the wired communication. Okay, so we see the difference now. Okay, so and again, this is because of the fact that wireless is always a shared medium. It's always a shared medium. So in wired, if you have two persons are communicating, okay, through wired signal, okay, there is S1 and there is D1, and there is S2 and there is D2. Okay? If both of them are using wire, are they affecting each other? No. So just cut this and use wireless. Are they affecting each other? Yes. Why?
Same medium.
Because it's the same medium. Okay? If you have wired, it's different. Well, this fundamental issue with wireless makes it really hard to control the sharing of that medium. Okay? So we know that there is, even in wired, there is some scenario where you need to share the medium if you're using a shared bus. If you're using like a shared bus and everybody's connected to it. Okay? So this is Ethernet. So Ethernet is a standard for shared medium. So if two people are sending, there is collision, right? But all the people who are connected on this shared bus, they will share the medium. So we know that. That's why there is Ethernet. In wireless, it's even more challenging. Because even if two people are, or two parallel communications that are far apart, they are still sharing the medium, whether you accept it or not. So and you need to control the sharing of that medium. And guess what? For the case of Ethernet, everybody's connected to a wire, so you can select one of them to control or something, right? But in the case of wireless, they are distributed in nature, which makes really wireless as a domain of in computing really overlaps a lot with distributed systems. Why? Because all these nodes are distributed in nature, and you don't have really a centralized node per se. Whereas here, I can designate one of these nodes because all of them are connected on the same line. So I can designate one of these nodes to act as a centralized control and to organize. But for wireless, if you do this will lead to inefficiency, because these are mobile devices and they're supposed to be portable. So it's all about distributed systems. So controlling of the medium in a distributed way is a really challenging job. Versus, well, it's like when we are sitting in a meeting, okay? If we have one organizer to the meeting, then things will go smooth, right? Because if you want to control, you raise your hand and then you can talk, and the organizer or the coordinator can allow you to talk, right? So it's simple. So if you have a centralized control, you always make it simple. But if you don't have this centralized control, you may actually, two people may talk and the other people will talk, and there is always interference. So it will affect each other. Okay. So so the fact that it's shared medium makes security challenging and makes even the control of the medium really challenging. Okay. Any questions so far? So these are fundamental. Of course, each of these characteristics we'll go through them in more details later on. We have a whole chapter about medium control and how we control the shared medium using different techniques and things like that, whether centralized, distributed, and all of this we'll talk about. All right, so now we can talk about some historical component about wireless communications. I don't like the historical part, to be honest. It's my personal preference. So I always lack really memorizing dates. And in many cases, I don't care. But since it's covered in the book, we need to go through that. So it started in early 80s when in the States they came up with the AMPS, or Advanced Mobile Phone System. This is the first generation. We call it Generation 1. So first generation was called AMPS, and it was standardized originally in the States. And this was completely analog. Completely analog, which means that there is no digitization of the signal. There's no modulation. There's no. We'll talk about modulation and these things. There's no channel coding. And, so it's pure analog communication. Okay. So it's based on RF hardware design, and there's no digital domain. There's no baseband digitization to the signal at all. So you just need to send the voice as an analog signal, and just send it in a specific frequency domain. That's it. And in that case, as you can imagine, there is no data transmission at all. It's used purely for voice communication. So the headset will convert your voice into an analog signal, which gets transmitted over the air as an analog signal. So the physical layer in that case is very simple. It takes the analog signal, transmits it through the air. That's it. No data associated, nothing. Okay, so in 91, they started the standardization of digital enhanced cordless telecommunication. It started with digital enhanced cordless phone or telephony. And later on, they changed telephony to telecommunication. Why? Because telephony is related to only voice communication. But telecommunication here is broad. So it implicitly indicates that this is for voice communication and also for data. But the data rates, as you can see, data rates here is really, it's like 120 duplex channels. So of course, this is partially digital, as the name suggests. So unlike AMPS, DICT is actually digital. So it's partially digital. It's not fully digital. It's partially digital. Okay. So there is some digital domain. In the digital domain, you can really divide the baseband into 120 duplex channels. So these channels, they are used in combination to transfer the voice information. Okay. So again, you digitize the voice, and then you send this voice across multiple channels. And so the standard defines 120 duplex channels. When it says 1.2 megabits per second, that the data transmission and voice transmission. The data transmission in that case is lower than this. Is lower than 1.2 megabits per second. Okay. There are some voice encryption, authentication, and things like that, which is again trying to address the issue of security, which is not the scope of the course. And it supports up to several 10,000 users per kilometer. So it really supports dense type of network where you have really tens of thousands of users in a specific 1 kilometer range. Okay. The real revolution in mobile communication started from second generation, really, when they came up with the Global System for Mobile, or GSM. So GSM is the real kick-off of mobile communications, which really revolutionized the mobile communication domain. So they added the definition of 124 channels. Here there is a support of data transmission of up to 9.6 kilobits per second. As you can see, the data part is really low. Okay, and nobody has actually used it except for some fax and some very high-level service. But it was not used for actually data transfer like what we have nowadays, because really with 9.6 kilobits per second you cannot actually have any reliable data transmission. But the kick-off for GSM is that it supported roaming. Okay, so roaming was the actual kickoff. The fact that I can take my mobile and move from one location to another and get covered by different base stations, and even when I move from one country to another, I also can get coverage while I'm traveling or something like this. So this was the real revolution, really, because DICT did not support handover or roaming from one location to another. So you have to be in range to the other device in order to communicate. And again, this range is, we're talking about here, a range of still pretty far. So within that range, you can have good communication. It's device-to-device communication, okay? But there is no, if you are not in the range, then you cannot talk, that's it. But now with GSM, you have towers everywhere, and you can move from one location to another and get coverage, which is what they call roaming. Okay, so you can roam, you can hand over your service from one base station to another, and that was really the key for the spread of GSM, and that started in 1992. And of course, because here we signify the notion of location, so you have some automatic location and handover mechanisms built into the standard to allow the network to locate you anywhere. And here, localization is done that you are in the range of this base station or this base station or this base station. Not that we have the latitude and longitude of your location. No, the localization here is the fact that you are now connected to this base station or this base station or this base station. So we can get your location in terms of which base station you are connected to. Okay, not as exact location as latitude and longitude. Okay, and again, data service was really low. So that was the second generation. In parallel to this, we had the standards for Wi-Fi. Well, we know that for cellular networks originally was designed for voice communication, originally, okay? The data channel, which supports 9.6 kilobits per second, was really not the significant part of the standard, but it was mainly designed for voice communication. In parallel to this, there was the Wi-Fi standards, 802.11 family, that came in '97, and these types of wireless standards, they cover the data part of the data communication. Okay, so they were not designed for voice communication. They were designed originally for data communication. Okay, So that's it, to understand the difference between the two types of standards. So there is a huge difference between the two. This is for voice and this is for data. So because Wi-Fi works in a shorter range, relatively speaking, like for cellular communication, we're talking about, for GSM, we're talking about a range of up to 500 meters. Okay, so you can be in the range of 500 meters to the base station that you are connected to. So it covers pretty large area. Whereas for Wi-Fi, the range is significantly shorter than that. We're talking about a range of maybe 100 meter maximum, something like this. Okay, so so in that case, you need Wi-Fi was designed for data transmission to cover a locality or a small geographic area. That's why they call it local area network, wireless local area network. Okay, so of course for Wi-Fi you get connected to an access point. So we have access points here everywhere, and we can connect to them. Originally, of course, for the first type of standards did not support again any roaming or handover between the different access points. So here, like here in the university, for example, I can move from access point to another access point, and it's still the same network and stuff. So this was not part of the original standard, of course. But later on, we have. So you see that you always have two branches. You always have cellular communication and Wi-Fi. Those are two branches. Okay. So you can think of them as. So you have cellular communication, and you have Wi-Fi. Okay, this is originally for voice, and this is originally for data. Why I say originally? Because nowadays they started to converge. So for cellular communication, we started to see data transmission, and for Wi-Fi, we started to see some voice communication, like IP telephony and so on and so forth. So really, each team who is advocating a specific technology, specific wireless technology, they started to incorporate some of the features from the other team to make the technology more and more usable. Okay? So GSM, as we said, the first set of standards worked in the 900 megahertz frequency range. And when we say a range, when we say a range using one number, what we mean is actually this is 900 megahertz. But the signal spans a range of frequency. So when we say at 900 megahertz, we mean that the center frequency of the signal is 900 megahertz. Okay, but this could be like 910, and this could be 890. Okay. So GSM worked originally in the 900 megahertz. Wi-Fi started in 2.4 gigahertz. In 2.4 gigahertz. And in the infrared range, we'll talk about the range of frequencies later on. The first standards of Wi-Fi again supported pure data rates of 2 megabits per second. Well, this is originally designed for data transfer, so the data rates must be really high. And the fact that, again, in WLANs, we're talking about shorter range, so you have the possibility and the flexibility to have high data rates. There are, of course, many proprietary products and mobile devices that support Wi-Fi, like our mobile phones and things like that. Okay, so in 98, the GSM started to have the next version, which is what we call UMTS. UMTS, or they call it IMT 2000. UMTS, or Universal Mobile Telecommunication System. This is the beginning, and here we're talking about the specification So there is a difference between the specification and the use of the standards. So the specification came out in '98, but it was not realized in real mobile products until 2001. So we see that. So there is in '98 we have the specification. Okay, but G3, the third generation, came around 2001. So there is at least around 2 years for the specification to get realized into actual products. So UMTS is the standardization of third generation mobile networks or cellular networks. So this was in Europe. Again, GSM was originally standardized in Europe, not in the US. So unlike AMS, AMS was standardized in the US, and GSM was Europe. And later on, GSM has become the de facto standard worldwide. So even in the US, they also use GSM. Okay. So in '99. The wireless LAN team or Wi-Fi team, they started to again standardize other versions of Wi-Fi. This time it's not 802.11, the base standards. They have come up with more versions of the standards like 802.11b and 802.11g and 802.11a and so on. And there are still, other standards that comes until nowadays. So nowadays we have 802.11ab and AC, and so we started to even run out of first letter, so we started to have 2 letters. So there are many versions of 802.11 family. And actually, even with Bluetooth, which is 802.15.4. So Bluetooth is 802.15. Standards also came after 802.11b. So the different variations of the 802.11 family vary in terms of the actual transmission rate supported, the frequency range that it uses, and some other techniques like modulation and things like that, which we will talk about later. Okay, so watch for the difference between specification and standardization. When I say specification, this is the release of the standard document. When I say standardization, this is it's like the go live. When the standards actually becomes available and it's actually manufactured or built into some mobile devices. Okay. All right. So Wi-Fi has motivated the cellular communication standard team to start building or integrating some data services in the cellular telecommunication standards. It's because GSM supported only 9.6 kilobits per second, and that was basically not enough to provide any kind of significant data services. So in 2000, started to talk about 2.5G. The 2.5G is an intermediate generation between 2G and 3G. Right. So what happens is that GSM originally was mainly based on circuit switched network. By circuit switching, we mean, are you familiar with circuit switching? So circuit switching, we mean that you have to establish a circuit end-to-end before you start communicating anything. Okay. The good thing about circuit switching is that you can get deterministic quality of transmission because it's like you have a pipe. You establish a pipe first and then you send the water through the pipe. So if you establish the pipe first and then you send something through it, then it goes smooth, it goes in order, and so on. Unlike packet switching, which it goes through the router, and the router may select to forward it, may select to send it to other routers, so it goes through different routes and so on. So the delay is not deterministic, and they may arrive unordered, and so on and so forth. Okay, so voice requires some deterministic delays because it's a real time signal. So you need some kind of circuit switch support to provide good quality on voice. So GSM originally was circuit switch. The problem with that is that I have to establish an end-to-end circuit, right, before I start communicating anything. So imagine if I have if I call somebody, I dial the number, I establish the circuit, and I leave the mobile number and go away. What is happening now is that I'm still using the circuit. I'm not using it, but
you reserve it.
But I'm utilizing it, right? So this is inefficient, right? This is one good thing about packet switching. It's packet switching. If you're not sending anything, you're not utilizing it. This is the major difference between the two. So GSM was originally circuit switched. And that's why we get charged by the second or by the minute, even if we're not saying anything, right? Whereas for data, we get charged by what?
Data.
By the packets that we send. So if we're not sending anything, we don't get charged. So this is a major difference. So they started to think about some ways to provide data services over circuit switching. The problem with that is that if you're opening a circuit and you're not sending anything, you're utilizing the resources of the network, and this is not efficient. But they cannot move completely from circuit switching all the way to packet switching. Because they have to change the hardware, they have to change anything, they have to change everything. So what happens is that they came up with 2.5G. They came up with 2.5G, whereas they have introduced new channels for GSM. Initially, these channels were high-speed circuit switch data. So this is the first 2.5G standards. Again, HSCSD is an integrated part of it's like amendment to the standard. It's not a new standard. It's an amendment to the GSM standard. Unlike UMTS. UMTS is a whole new standard. Do you get the difference? So HSCSD, it's a new component in the standard that gets built into the GSM standard. Okay? To support data services. So what they did is that they have introduced, in addition to the 140 channels, 124 channels that GSM defined, they have introduced other channels, again, still using circuit switching, but these channels are dedicated for data services, not for voice. Okay? And they supported data services of up to 57.6 kilobits per second. Well, this is a major upgrade, right? We were talking about 9.6, now it's 57.6 kilobits per second. So this is a major upgrade, okay? But it's still circuit switched.
Yeah, but it's specifically for data.
It's specifically for data, exactly. So it does not it does not get used for voice communication, so it's dedicated for data. But still circuit switch, because again, transitioning completely from circuit switch to packet switching, this requires major change of hardware. So the good thing about HSCSD is that it's just a software update to increase the number of the channels and dedicate some other channels for data communication as opposed to voice communication. So the amendment was not that major. Okay? And then they introduced Gprs, which is some of us are familiar with Gprs. Gprs is the trial version of using packet switched channels over circuit switched networks. Okay? So Gprs required some hardware change. Okay, so Gprs required some hardware and software change, and this is packet oriented or packet switched transmission. Okay. So the data rates in that case is comparable to CSD, but it's on packet switch domain, which is more efficient because using HSCSD with data rates 57.6, again, if you are consuming the virtual circuit, even if you're not sending anything, you're utilizing the whole circuit, which is not efficient. So Gprs with 50 kilobits per second is more efficient than circuit switching with 57.6 kilobits per second. Because more efficient, of course, because Gprs allows the sharing of this medium, the sharing of this bandwidth amongst multiple users efficiently. If one user is not sending, the other one is sending, so I'm actually allowing for the sharing of the medium more efficiently. Whereas with the case of HSCSD, if someone is sending, he is utilizing the entire virtual circuit. So even if he's not sending anything, he's still utilizing that. So it's not really efficient. Okay.
So it's efficient in the term of scalability.
Scalability, yes, you're right. Yes, that's a good word. Yes.
And also the other utilizing the resources.
Yes. So it's in terms of sharing the medium, packet switching is always more efficient in terms of sharing the medium, because I'm not utilizing the circuit if I'm not sending anything, which allows multiple users to share the medium. If one is sending and the other one is not sending, they get good pair of data transmission, and they can share it more efficiently. Okay. Then came the G3 or third generation, which actually is related to this specification. So this specification came live in 2001. This actually came, the specification on 98 came live in 2001 to start using UMTS, and there were some versions of these standards in Korea, in Europe, in the States, and so on. So in Korea, they used what they call CDMA. So we'll talk about the difference between CDMA and FTMA and TDMA and all this. Okay. So the version of the standard that uses CDMA was first standardized in Korea, and then UMTS, which is based on FDMA and TDMA, again we'll talk about that, was actually standardized in Europe and parts of the US. Okay. And also Japan.
When we say specification, does this mean that we do have...
It's the document, the release of the
only
document. Yes.
But not applying it.
But not applying it, yes. Now we're applying it. Okay.
So on 98 and...
From 98, yes, to 2001, yes. It took 3 years, yes. Takes even... Well, we have some standardization for fifth generation now. We have G5s. Some documents of the G5 standards is released. But we're not actually hearing about that because until it gets realized in actual devices, this will be at least 3-4 years down the road.
But what if the resources since that time until today is we have different
yes,
resources,
but it just takes
techniques,
time
so
to standardize. Yes, it takes time to standardize things and to put some concepts and mechanisms into productization. It takes time, just takes time. You cannot just skip that. So it starts from research. Research will come up with mechanisms. These mechanisms will get will affect the standard. The standard will be released. Everybody will know about it, and then many companies, they will start adopting the standard in their products. So this process takes time. Yeah. It doesn't happen overnight. Okay. Right. Of course, the struggle between cellular communication and Wi-Fi is still on until today, and I think it will last long because Wi-Fi is not giving in anytime soon. Some other branches for cellular standards came about in 2005. Well, right before that, we started talking about wireless LAN hotspots. wireless LAN hotspots is the standard that allows Wi-Fi to, this is what I was talking about. So it allows people to deploy access points in airports, in many locations and stuff, and it allows for roaming between the access points. So I can build a network of Wi-Fi, which all these access points, they belong to the same network. And in that case, as a user, I can move around. So this way, I technically increase the range of Wi-Fi, and I can deploy it in airports, in here and there, in businesses, in malls, and so this actually started to contribute to the fact that the Wi-Fi has spread in many. So before that, we were actually using it in short range, in a small LAN at home or in small business and stuff, by using the hotspot and the fact that I can roam around the access points. Now I can deploy it in many large places and stuff. So after that came the WiMAX. WiMAX is another branch of cellular standards that they started to initially provide some replacement to the internet service. So, so at home, you were supposed to have a WiMAX device directly from home, and you have the internet access, because WiMAX, similar to cellular network, has long range. So WiMAX supports 500 meter long range. So you can think about it as a replacement for cellular standards like UMTS. Okay. But WiMAX, they came with the concept of providing internet services to home subscribers directly. So they replace the DSL, you know, the ADSL, the digital subscriber line that we used to use. Nowadays, of course, we are blessed with the fiber optics and so on. But before that, we used to use the DSL. So WiMAX has lost ground completely. So again, there was a struggle between the UMTS standards and WiMAX, and that lasted for years. But thanks to LTE, or long-term evolution. Long-term evolution is the next generation of UMTS. Okay, so LTE is the extension of UMTS, which supports 3.5G and 4G. We'll talk about LTE standards later on. LTE came into play and wiped out completely the WiMAX, almost completely. So WiMAX has lost ground completely to LTE, because LTE has all features of WiMAX and even more, and it's compatible with GSM, which the market was dominated with GSM already. So all the GSM devices, they can use LTE, okay? But WiMAX, the problem is WiMAX was not completely compatible with GSM. So all devices have to change to use WiMAX. But LTE came with backward compatibility with GSM, and that's one of the features that led to the fact that LTE has dominated the market. And I'm not aware of many companies that still use WiMAX nowadays, but it's very, very limited used. Okay. So LTE, they started to have some internet service provisioning, and nowadays we're talking about even LTE for 5G, which will replace ADSL completely. LTE came after, as I said before, between 3G and 4G, there was again 3.5G. Similar to 2.5, there were 3.5G. So there is HSPA and HSUDPA and things like that. There are some variations that came with the UMTS, which we will talk about later as well. And these started to provide data rates of more than 100 megabits per second. So from the 50 megabits per second, 50 kilobits per second, we started to see hundreds of megabits per second, which is also major outbreak. So that actually opened the door for many companies to provide services over these types of technologies, whether it's voice over IP or video on demand and things like that. Some applications that require really high data rates. Okay. And of course, starting from 2010, we started to see more LTE devices for 4G, and LTE started to sort of get grounds from GSM. Of course, it's backward compatible, but many devices we started to see like smartphones morphing or transitioning into using 4G nowadays. So the number of subscribers worldwide for GSM was really, really high. We'll see that in a minute. It was really, really high at some point. And starting from 2010, LTE subscribers, they started to gain more ground from GSM. Because of the fact that both of them can work using the same network, right? Because LTE is backward compatible with GSM, right? So GSM subscribers can still use LTE network, and of course they will get lower data rates, but at least they can operate, okay? And devices that support LTE allows mobile devices to support high data rates. And of course, LTE as well started to provide some DSL replacement for internet service provision. So that device shows us the evolution of the different wireless technologies, different wireless and mobile technologies, and even wired technologies across the different years. So we can see that, for example, so active broadband subscriptions. By broadband here we mean supporting data services over cellular network. They call it a broadband subscriptions. So broadband subscriptions in 2006 was none. As you can see, there's none. And then in 2010 we started to see more of this. I think this is in the range of millions, and so it's not one subscriber. It's like we're talking about millions. The fixed wired broadband. So this is the subscription in terms of DSL and some wired technologies like DSL and things like that. So this is growing, okay, but not with the same pace. So this is fixed telephone lines. Fixed telephone lines here, we're talking about public switch telephone networks, the landlines that we have. So fixed public switch telephone networks, as you can see, started to flatten out, and nowadays it's actually even going down. So we're starting to see more and more people are, switching to completely mobile. So I have a mobile device. I don't have to have a landline at all. Okay. So that started to flatten out, or even nowadays started to go down. Internet users, we're talking about the normal internet users, and that's also growing. But we can see that mobile cellular telephone subscription, this is growing really rapidly. So this is growing exponentially nowadays, and of course it will continue to grow because nowadays the same device can support voice communication, can support data communication, and so on and so forth. But what we are expecting to see in the near future is that this black one will go even higher. Will go higher rapidly.
Is the black one?
The black one is the broadband subscription. So broadband is like data services over cellular networks. Data services
like
over
WiMAX?
cellular. Not WiMAX, no. This is supporting like 3G and 4G with data plan.
Okay. That is the same as mobile cellular network. It's the same thing as
Mobile cellular network, but used for data transfer, not for voice. Okay.
Is there any
So
operator operating like that?
yeah, Orido, and yeah. So we have data plans, so we can use data plans on our mobile phone now, right?
So have they segregated data voice like that?
Yeah. Well, there is data services and there is voice services.
Okay.
So voice subscribers are growing, and they will still grow.
Okay.
The data subscribers.
We
Data
segregated.
subscribers means that I may have a mobile phone that's used minimum for voice, right? But I may not have data plan. But this tells us we started from zero here in 2006. We didn't have any data subscribers. Okay? So nowadays it's growing, and it's growing fast. And actually in the near future, it will get very close to this. It will get very close to this, because everyone on earth who has mobile phone, he or she will have data plan. Okay? So this is growing actually exponentially, thanks to 4G and later on 5G. So we will have more and more data services over cellular networks. And people are starting to talk about, again, getting grounds from even Wi-Fi. So if I'm roaming, if I'm traveling, and so on and so on. So now I can get Orido passport, I can travel everywhere, you know. I land in the airport and I use data services and I pay, you know, very low cost. 100 Riyal, I can have 1 week of roaming and moving around worldwide, and I can have very nice, good data services. I can do WhatsApp, I can do Wi-Fi, I can do Skype, voice, and I can talk to my relatives and stuff. Okay. Wi-Fi, the problem with Wi-Fi, it does not provide roaming across countries, so this is very cool. So so people started to question themselves now. When do I need Wi-Fi? Well, it turns out until nowadays we still need Wi-Fi for hotspot kind of coverage. If I land in the airport and there is I don't have data plan or something, so I may have actually some free hotspots here and there. So it started to get really limited use. But the more broadband services we have, the less we start to use Wi-Fi. But until maybe in the near future, some time down the road, we'll still be using Wi-Fi. So we still have some usage for Wi-Fi. So this is how it looked like. Again, this is pretty old. This is since 2008 and 2009. And as we can see, there is a huge peak for GSM compared to all other technologies, right? So GSM is really the predominant standard in 2008, 2009. Of course, if we were to do the same chart today, we can see that here there is, well, even the technologies, we don't have any UMTS. But if we were to use LTE somewhere, and this is like 2016, then we should start to see some comparable types and peaks for LTE, which maybe it started to dominate even more than GSM, or at least comparable, right? Any questions?
But in the previous slides, we talked about WLAN.
Right. Wireless LAN.
Yeah, wireless LAN.
Mm-hmm.
That is a local thing, no? Like,
right, yeah, it's called local area network, wireless local area network.
And
right.
Is it connected with a backbone like if...
Wired.
Wired.
Wired. It's connected as backbone with wired networks.
We can provide a WLAN in airport, which is
right.
connected to the same
wired
backbone,
network, right?
And in another college, which is connected to the same backbone. So
right.
there's a wired network backbone, and then we have
wired. Right. Right. But with the cellular network, why do we need to have this? Is because the Wi-Fi range is relatively short. We're talking about 100-meter range. So we need to have a backbone which connects things together. And with the new standards, at least now we can roam around the access points and we can still be connected to the same network. So this is good. This is good. But still there is no roaming across countries. So we cannot use it for broadband communication with very large ranges. With cellular networks, not only do we have very 500-meter range, but these towers, they act as our backbone network and they cover the whole country. So regardless of where we are, we're covered. Okay. Not only that, even if we move to another country. There are some agreements between the cellular providers to provide you service in the other country.
Internationally.
So really it started to get really mature, and there is all the regulations and agreements are mature, and they are in place to make your life easier. So that's why it's attractive nowadays to many people. This is what concerns us as researchers, potential researchers. So if that's the case, understanding all these standards, so what are really the potential areas that we can contribute to as researchers? And here, remember that we're talking about wireless communication, from wireless communication point of view. Of course, there are other research areas in application layer and network and TCP and transport and stuff. But here, we're talking about wireless communication, which covers potentially the physical layer and data link layer only. Okay, so for wireless communication, transmission quality and spectrum efficiency. So by transmission quality here we mean, so we need to guarantee that the wireless signal itself has low quality. Some people are working on directing the wireless signal to try to avoid obstacles and things like that. So we know that the wireless signal travels across the air, but can we actually increase the strength of the wireless signal in certain location, and weaken the wireless signal in other locations? It turns out, yes, we can do that, and that's what we call beamforming. So we can direct the beam of the wireless signal towards a specific location, and if we can do this, well, again, this is very sophisticated to do in terms of hardware design, but if we can do this, then we can increase the transmission probability and the transmission rate in a specific direction. And this is what we call a beamforming. So I can actually like point
What we call
beamforming. So I can increase, it's like you are directing the wireless signal towards a specific person. So if I direct the wireless signal towards you, then you get the best quality, right? But this will come with a cost that other people, they will get low quality, right? So the question here is that, can I control this direction of the beam so that I can guarantee the quality for a particular person? Well, if we have some cross-layer design where we say that we want to control the medium, that, well, Abir will have access to the medium now, okay? Which means that she will have the right to receive packets, okay? Which means that others will not receive the packet. Well, the physical layer will say, okay, so if that's the case, then I can direct the beam towards her so that she can get the best quality, okay? And this has to be done, real fast, in real time, and there is some difficulty and some design aspects associated with this. It's not that easy. Okay? Spectral efficiency talks about the fact that, well, we know that the wireless signal will be sent in a specific frequency range. We call it the bandwidth. Okay? The wireless signal itself travels in, or uses or utilizes specific frequency range. So this is the frequency, okay? Spectral efficiency talks about the fact that how much data rate I send over a specific frequency range. So I can use different modulation and encoding mechanisms and stuff to digitize or to represent the digital signal using wireless signal in a specific frequency range. Okay? So spectral efficiency talks about the fact that the more data I can send in this bandwidth, the better. Right? So nowadays they are talking about very, very high spectral efficiency in 4G and 5G. So using the same bandwidth, which is around 20 megahertz. So the typical bandwidth of the wireless signal nowadays is around 20 megahertz. So in this 20 megahertz, you can send 300 megabits per second. That's huge. You can send data rates, and that requires really sophisticated modulation schemes, encoding schemes, and stuff. So that's an area of research. So spectral efficiency is an area of research. And that, again, combines with modulation, encoding, and interference mitigation techniques. So beamforming is used for interference mitigation. Okay? So if I'm communicating with a person and I can do some beamforming, then I'm actually reducing the effect of interference. Because if you are strengthening the wireless signal in a specific direction, this means that the effect of the interference will not be as strong as if you affect a weak signal. So of course, if you have a weak wireless signal, any interference would affect it negatively, right? But if you have a strong signal, the interference will not affect it that badly, right? So using beamforming, I can also have some interference mitigation. Modulation talks about the fact that I can represent the digital signal as values using amplitude shift keying, phase shift keying, or frequency shift keying, and so on. We'll talk about this, in details as part of this course. So digital modulation is a good component of this course, and of course using different types of modulation techniques. Again, we can have probability of error, and we can affect the probability of error, and we can affect the interference and stuff. So all these techniques actually, they are in a way combined together. Coding talks about the fact that so if I have a digital signal, which is like a symbol is like ones and zeros, and at the end of the day, our data gets converted to ones and zeros. Okay, so we can get a specific code word like 101, and then we need to send it over the wireless network. When we send 101, we need to send it as analog signal. At the end, we need to send it as analog signal. Before that, we need to do something called coding. And by coding here, we actually code the 101 into another stream of bits, which could be 1101. So why do we do this? We'll study in this course. Coding is a very important component in digital telecommunication systems because it affects the probability of error. So the very simple example for now is that if you have a stream of zeros, if you want to send 0, 0, 0, 0, okay, some signaling technique 0, 0, 0, 0 would be converted into a signal with 0 volt. So can you send a signal with 0 volt? In that case, any noise may get may get higher value, and you may actually understand that this is 1, not 0. Okay. So if you have a 0 volt, any error will be very prone to error. So what happens is that instead of sending 0, 1, 0, 0, 0, 0, they actually put ones on purpose in the middle to reduce the probability of error. And of course, there is some estimation of the probability of error for each coding technique, which we will touch it a little bit, not because this actually related very much to information theory and things like this, which is not the main focus of the course. But we'll talk about some of these things. Interference, we talked about it, of course. Radio resource management. Radio resource management is a data link layer. We'll see all these techniques with respect to the different layers in a second. Radio resource management is a good component of this course as well. We'll talk about it a lot. And radio resource management here talks about the fact that if you have multiple devices, multiple wireless devices, how well our channel is, we have like 20 megahertz. The 20 megahertz, we can divide it into smaller channels. We can divide the 20 megahertz into smaller channels. So radio resource management talks about the fact that which channel do you allocate to a specific communication between these devices in such a way that you reduce the interference between them. So you can control the interference a lot, and you can have really, you can maximize the capacity of the whole system just by controlling, allocating channel between the different users. Because if you know that you have two communications that are close to each other, if they use the same frequency range, they will interfere with each other. So I can use here channel 1 and here channel 2. Versus if this communication is really far away from each other, I can use the same channel here and there, and they will not affect each other because the distance is really high. So they will not interfere with each other. So if you have a very big network, just by controlling the channel, you can minimize the effect of interference, which means that you maximize the capacity of the entire system. So radio resource management is another, and this actually touches on distributed systems a lot, because, well, you have multiple distributed wireless nodes, and you need to allocate the channels here and there in such a way that you maximize the overall capacity of the network. Okay. So these techniques actually, they are arranged in physical layer and data link layer, as we will see in a minute. Mobility is a whole new dimension, because if the system is moving, if the person is moving, I have to control the location of that person, and based on that, I need to change the services based on his location. For example, there is a big research about handover. So if the current network is allocating certain resources to this person, and the person is moving, when do I take out these resources from that person and say he's not in my domain anymore? Because if I do that prematurely, he will lose service. He will lose the service for some time. Imagine like a person is actually driving a car, and he's talking over the phone. The last thing that he wants is for his phone call to be dropped, right? So this handover needs to be done really carefully. Because if I do that prematurely, the voice call will drop. But if I don't do that fast enough, I'm allocating resources which this person cannot use because he is in the range of another base station. So there is a trade-off now. If I do it prematurely, I will affect his service badly. If I don't do it fast enough, then I keep the resources utilized by a person that he cannot use it. So handover is one of the issues in mobile communication, and it's very critical. So there is soft handoff, hard handoff, and so on, and it's a big domain. Okay. Quality of service support. How can I provide a different quality of service based on the traffic of the person? So, for example, if I know that you are using a video application, I need to give you, in a certain period of time, I need to probably give you more bandwidth and more resources of the network, because if I give you less, then the delay will be high, and if the delay is high, you will get very terrible service. You will not be satisfied. Versus if he is actually transferring a file over the network, he may tolerate certain delay. There is no problem, right? If he's downloading a file or uploading a file, it's fine. But she's streaming a video. Any delay would affect her service. So quality of service is a big area of research. How can I give each one resources based on the type of the application that he's using? This is a major research area. In fact, in my group, we're concentrating a lot on quality of service issues. So quality of service can be represented using delay guarantees, jitter guarantees, security guarantees. Okay, so I can guarantee certain security level for the person based on the application. If she's actually transferring money over the network, okay. Well, while he's browsing the internet, well, I better give her high security levels more than him. So this is part of the quality of service. So how can we quantify this quality of service? How can we guarantee this quality of service based on the different users and the different applications? That's a major research area. Okay. And of course, we have the issue of portability. Actually, in fact, each one of these issues is a course on its own. Just to be clear, and we can design a course based on only one of these words. Okay. Portability, we're talking about power consumption. Well, nowadays, power consumption is a huge research area. We're talking about renewable energy. How can these devices harvest energy from the environment? We now have products that allows you. You can have a wireless router at home that can charge this while you are moving around the house. Charge this over wireless. So you're not using this for voice and data. You are also harvesting from the wireless signal, because guess what? I mean, the wireless signal itself has power.
Yes.
So you can use the receiver here, to get the data of this wireless signal, or to get the power of the wireless signal. But you have to get either. If you get the data, you cannot get the power. Okay.
But how we get the power?
Yes, you can. Yes, you can harvest from the. There is some hardware here that allows you to. Well, there is wireless chargers, right?
Yeah.
So it's the same idea, but this is through a range of wireless signal. So the wireless signal itself has some energy. So here I can get this wireless energy and charge my battery, okay, and skip reading the data for now. So this mobile device can harvest energy from the environment. Not only that, of course, we can use of course solar cells. We can use this and that. We can charge our equipment like for smart grids, and smart grid it's a network. It's a smart network at the end of the day for devices that connect to each other. It's wired, but they are deployed in the environment. Maybe parts of it will be wireless, and in that case, we need to charge these devices maybe through solar cells and so on and so forth. But even without renewable energy, because renewable energy is a field, but power consumption, if we know that this is a battery-operated device, we need to really watch carefully where do we use the power and where do we use the energy of the battery, right? Because if we use it less wisely, we will drain the battery fast. And that's why I'm biased through iPhone. I'm biased towards iPhone, but iPhone can last for 2 days versus like any Android phone, maximum 1 day. You can use this smartly. It's not about using a bigger battery only. No, it's about where do you allocate your power. Okay? So for example, if I know that I'm very close to the person that I'm trying to communicate to, why use the same amount of power when I communicate to a person who's far? So I can, but this requires that I need to know the location of the person that I'm communicating to. If I know that, then I can allocate the power. And here comes the intelligence and the smartness. So if I can allocate the power based on the distance. But I need to know the distance. How do I know the distance? Okay, so that's a whole new field. And whether we're talking about Wi-Fi, ad hoc network, mesh networks, cellular networks, what power consumption becomes a real, even for towers, even though towers, they have their own, systems for powering them, but nowadays they power them through motors. They power the big towers through motors. So still, I need to increase the lifetime of these power machines. So they are talking about green communication now. Green communication is a whole new field. So if I'm in an area and there is no user who is actually using this tower, why does the base station have to send beacons and pilot signals and stuff across the entire range to announce the fact that there is a base station in this area? Okay, so green communication talks about the fact that base stations have to be smart enough. If no user is around, then it can actually go in a sleep mode. But the problem about sleep mode is that you cannot control when do you wake up. So
What we have used it.
in order to detect that there is a user, you have to wake up.
Awesome. Right.
So this is the real problem, right?
Or
So the only way is to adjust the alarm and say I will wake up I will sleep I will have a quick nap, but again you don't have a guarantee that during this duration no user will come into the picture and try to get some service, and actually if he wants the service and he doesn't get it, then it's a problem. So green communication is a whole new field. So how do we do this? And 5G, it becomes even more problematic because in 5G, we're talking about big towers and small towers and smaller towers. So we will start to have our base stations at home. So there is femto cells, there is pico cells, and there is macro cells. So we're talking about very dense network. So the base station can go into sleep, and the pico cells can still serve the users. So how can we adjust and control who sleeps when? This is a huge field. Doing some, again, this is part of radio resource management as well. So we can talk about sleep modes and stuff as part of radio resource management. So we can control when to sleep, when to wake up. We can actually reduce the spectrum at certain point. When we reduce the spectrum, again, we reduce the energy. So instead of using this range, we can use smaller range. So when we use smaller range, we actually save energy, right? So when can we tighten the range and when we can make it larger? If we tighten the range, then the capacity of the system will be reduced, which will affect the service of the person. Okay? When we make it larger, we can serve more users. So we can make it large or small based on the load of the users, and this way we can save power. Okay. So huge diversity in terms of research. So usability, again, usability talks about the fact that the display. So if we don't use again, this is part of power control or managing the power of the device. So if I leave a power unused for quite some time, then the whole thing, blacks out because the display is the most power consuming component of the mobile device. After the display comes the communication. Energy consumed in the display is number one. Energy consumed in the communication, number two. Processing energy is nothing. So if you run applications and use all the CPUs inside this phone, this does not consume any significant energy compared to using communication or using displays. So power consumption affects the usability, because if you left it like this, you are reading something and all of a sudden it blacks out, so you feel irritated. Right? So you have to always watch for power consumption with respect to usability. And there is a big trade-off there. Right? Any questions? Okay. So we'll just cover this and close. So this is the stack of the cellular system. So as I was talking, so this is the wireless device. So this device is the mobile or the laptop or the phone that's connected to the cellular network, and it has all the layers from the application layer to the physical layer. All the techniques that we talked about exist in data link layer and physical layer here in all these devices. Okay, so radio resource management in data link layer, modulation and encoding in physical layer, and so on. We'll see that. There is another graph about this. So the mobile device has all the 5 TCP/IP layers, and then it goes to the base station tower. Again, similar to Wi-Fi, from the base station to the backbone, it could be either base station to base station communication, or it could be through some backbone wired network. Okay. Nowadays, it's actually base stations are connected all together. without any wired devices. And from base stations to base stations, they use what they call microwave communication, direct communication between the base stations. But in the past, they were using actually a wired backbone. So access points similar to, you can think of it as similar to routers.
Yeah.
So routers are layer 3 devices. So they have physical layer, data link layer, and network layer. Right. And from there, you have the backbone, which is wired, which goes all the way to the server on the other side, which in that case has all the layers. So the radio link.
That server is a switch.
No, the server. No. The server is whatever ultimate destination you want to communicate to. So, for example, if I'm watching a video, this is the server where the video is hosted, like YouTube server or something.
She meant the wireless, right? You meant the
No. This is
point?
this is the base station. This is the base station. This is the base station tower, and this is what they call base station controller. We'll talk about this. Okay, but this is the layer 3 device.
Both of them are layer 3 devices.
What?
The base station or layer 2 something.
This whole thing, you can think about it as one thing, and it's similar to the router.
Okay.
This is a big antenna.
Yeah.
It's a physical device, physical thing. This actually converts the microwave signal or the wireless signal into electric signal that goes into the wire to this device. And this device is actually a layer 3 device, which reads the signal, reads all the data, and then processes the data and then sends it over the wired network. Here it's wired, and we don't care about the network. Here there is the internet, and there is many things until it reaches the ultimate destination. Okay, and here are the mapping between the layers and the different techniques that we talked about. Okay, starting from frequency, interference, attenuation, modulation, radio resource management, we see it there, medium access control. So we'll talk about, so actually in our course, we'll focus here in this part.
The
As the
encryption can be done in both, right?
The encryption nowadays can be done in any layer actually, and even nowadays we're talking about encryption in the physical layer. There is a whole new domain called physical layer security, which did not exist in the past. So nowadays we're talking about physical layer security. So we do the encryption from the physical layer. Okay.
But doing it in the physical layer, we don't need to make any. Do we have to apply it in the application layer?
It depends.
It's already.
It depends. No, it depends. It depends. Sometimes, for some services, you need to provide encryption on 2 levels or 3 levels. So it depends on the type of the application and the criticality of the application and so on. It depends on so many things. Okay, so these are the techniques. Of course, we're not going to cover handover, localization, and the quality of service. These are covered through the course, the advanced networks course, and another course. So here we're focusing on this part only. Okay, so any questions so far? So we'll stop here, and we'll break for 10 minutes for prayers, and then we'll listen to you for the presentation. Okay?